Imagine a city where every vehicle, drone, signal, train, and pedestrian moves as part of one living system. In this project, we'll design the intelligence layer that senses, predicts, and rebalances urban mobility in real time for tomorrow's cities. So far, we've moved from agentic AI and human interfaces into bio AI and robotic swarms. Project 20 brings that progression into urban mobility, where vehicles, infrastructure, people, and logistics all need to coordinate in real time. The core shift is to stop treating mobility as isolated trips and start treating it as a living system. In a body, nerves sense conditions, blood carries resources, and the immune system responds to threats. A city can work in a similar way. Sensors, vehicles, intersections, transit, drones, and logistics fleets become connected subsystems. I provides the coordinating intelligence, reading movement in real time, predicting demand, and adjusting flows before congestion or risk spreads. The goal is not only faster travel, it is safer streets, better access, lower emissions, smarter energy use, and a city that adapts continuously. Urban mobility may look like one system, but today it often behaves like many competing systems. Cars, buses, delivery fleets, signals, parking, cyclists, and pedestrians each follow separate rules and incentives. That fragmentation creates familiar costs: congestion, wasted fuel, lost time, unsafe intersections, and land locked into parking instead of housing or public space. Even when one actor optimizes, such as a delivery platform finding faster routes, the citywide result can get worse. Re-architecting mobility means shifting from isolated decisions to shared awareness, coordinated flow, and system-level outcomes. Here is the architecture behind that shift. The physical layer is the body: cars, buses, drones, robots, bikes, pedestrians, and emergency fleets moving through streets. The sensing layer is the nervous system, using cameras, LiDAR, radar, and environmental data to understand conditions in real time. Intelligence turns that awareness into decisions, predicting demand, coordinating swarms, simulating outcomes, and guiding intersections at the edge. Finally, the transaction layer lets machines pay, verify access, and settle services automatically. Together, these pieces create a mobility operating system for the city. A smart city does not rely on one sensor. It combines many weak signals into a shared perception layer. Cameras, road sensors, connected vehicles, drones, and transit systems report what is happening in real time. Edge AI analyzes much of this locally, so decisions can happen quickly, even before data reaches a central platform. Computer vision can detect pedestrians, cyclists, vehicles, curb loading, lane use, crashes, and hazards. The point is not surveillance. It is to convert raw observations into anonymous movement intelligence that helps manage safety, congestion, and demand. Predictive demand intelligence moves mobility management from reaction to anticipation. The system absorbs signals from events: weather, school calendars, work patterns, tourism, emergencies, and transit delays. AI models convert those signals into forecasts: passenger demand, vehicle availability, curb occupancy, drone delivery load, charging needs, and congestion probability. Before action is taken, a digital twin tests likely outcomes. Then the city reallocates capacity by staging buses, repositioning shared vehicles, adjusting routes, opening curb space, or reserving chargers. Outcomes are monitored, so each intervention improves the next prediction cycle. An intelligent intersection works like a local reflex, not just a traffic light. Cameras, connected vehicles, buses, pedestrians, drones, and emergency vehicles all feed conditions into an edge controller nearby. Because the decision is local, it can react in milliseconds, extending a crosswalk, clearing an ambulance path, slowing an approaching platoon, or adjusting signal timing before congestion forms. The cloud still matters, but mainly for broader coordination and long-term optimization. The safety-critical moment is handled at the intersection, where delay is most expensive. Swarm coordination treats every vehicle, drone, bus, and delivery unit as an intelligent agent. Each one makes local decisions, such as changing lanes, joining a platoon, choosing a curb slot, or sequencing a drop-off. But those choices are constrained by shared city goals: safety, travel time, emissions, equity, and network resilience. The power comes from simple local rules producing coordinated movement at scale. The risk is unmanaged emergence. That is why the swarm needs boundaries, safety protocols, governance policies, and trusted communication standards that keep individual convenience aligned with collective performance. Static infrastructure assumes yesterday's pattern will repeat tomorrow. Dynamic infrastructure treats streets as flexible operating space. A lane might support buses during the morning peak, emergency vehicles during an incident, freight at night, and bikes or pedestrians during an event. Curbs become programmable assets for pickup, delivery, charging, accessibility, or staging. Signals stop following fixed cycles and respond to real demand. Roads also communicate with vehicles, sharing speed guidance, hazards, lane permissions, and energy availability. The city becomes more responsive without constantly rebuilding concrete. In autonomous mobility, vehicles are not just moving through a city, they are negotiating with it. A car may pay for charging, tolls, curb access, or a faster corridor. A drone may reserve a delivery window. A fleet may respond to congestion prices and choose a shared, cleaner route. The settlement layer provides identity, permissions, payment, and an audit trail, so machines can transact without constant human approval. But this economy still needs public rules. Dynamic pricing must improve efficiency without creating unfair access, exclusion, or hidden exploitation. The city's digital twin acts as a safe rehearsal space. Before crews change lanes, adjust pricing, reroute buses, or open drone corridors, the city can test the consequences in simulation. Imagine a stadium event during heavy rain with a transit delay. The model combines traffic, pedestrians, weather, emergency routes, and emissions, then compares options. Leaders can see which action reduces travel time, protects emergency access, lowers congestion risk, and keeps crowds moving. The value is not prediction alone. It is making better decisions before the street feels the experiment. A smart mobility system cannot chase one number, like average speed, and call that success. It needs a balanced objective function. Safety sets hard boundaries. Protect pedestrians, cyclists, passengers, and emergency movement. Flow improves reliability, not just vehicle throughput. Energy and climate goals steer routing, charging, and parking decisions toward lower waste. Equity and access make sure optimization does not quietly exclude disabled riders, low-income neighborhoods, or transit-dependent communities. The key is trade-off awareness. I should surface the consequences of each choice, so cities can tune the system around public values, not just efficiency. By 2050, the big shift may be from owning vehicles to accessing movement. In dense cities, autonomous shared fleets could arrive when needed, then keep circulating instead of sitting parked. That changes the land equation. Space once reserved for storage can become housing, parks, charging depots, delivery hubs, or public places. Mobility also becomes less separated. Walking, transit, bikes, small autonomous vehicles, drones, and robotic logistics can coordinate as one adaptive system. The goal is not just faster trips. It is a city that wastes less space, responds to demand, and designs movement around human life. Project 20 showed how a city can behave like a coordinated organism, sensing movement, predicting demand, routing vehicles, managing intersections, and exchanging value machine to machine. The big lesson is that autonomy matters most when systems work together. Next, we zoom deeper into quantum AI, advanced materials, clean energy, and climate technologies that define future infrastructure.